Let's continue with the idea of reliability, validity, and workability of the results. So we are talking about science and change in the section changing the world, and credibility, legitimacy, and salience are always important when you want to get people to act on your advice. So your science must have reliability, validity, and functional, meeting the purpose with functional ability depends on workability of the science as well. So we looked at reliability, validity, and we were discussing ideas on the metaphor of triangulation. Then we got into some philosophical word like ontological and epistemological assumptions. But coming back to practical things that we understand, let's go into display mode first, which should happen immediately. So we left here that methods used, how to do reliability and validity and ensure workability. Let's look at a few more aspects of it. With no direct access to with no direct access to reality, we cannot know for certain whether or to what extent a theoretical construction is valid, regardless of the quantity and quality of the empirical data. So in the lab setting or in a study, you may have collected a lot of data, synthesized it, and you have made some theoretical construction based on it, but then it has to be taken back to the field and given a reality check. However, we must still assess the validity of such a theoretical construction in However, we must still assess the validity of such a theoretical construction in relation to the adequacy of the collected empirical data. So data itself often may be insufficient. Assessment of validity is thus based on judgments about the compatibility of the theoretical construction or the empirical data supporting it with our assumptions about the world that are presently taken to be beyond reasonable doubt. So we have assumed certain things as almost axioms, and or secondly the likelihood of error given the conditions in which the theoretical construction was made. So you may have collected empirical data to theorize something, but the data itself may be collected in a particular context or conditions which may limit the validity of the theoretical framework. It's important to note that these are judgments whose own validity never can be established, so you can only get more data to see if validity can be violated. Validity is thus related to the collective judgment of the scientific community, which Kuhn refers to as a paradigm, and Said calls an academic research consensus. This is very important because we have now many climate models across the world, with every country running multiple models in many cases, and when the models agree with each other, we say that must be true, especially going into the future. In the past, if we are very far from observations, let's say in terms of the warming or changes in rainfall or extreme events, we cannot claim that the models are right unless the data is really unreliable. But when the data is sufficient to make a validation and reliability of models as an assessment, then you cannot claim it. But into the future, you are assuming many things on scenarios, and then if the models agree, you may say, wow, that looks like the correct answer. So definitely academic research consensus can be tricky. In short, the purpose behind the ideas of reliability and validity is to provide grounds for someone to trust the research results. This makes Ramsey's idea of a reliable process central, as it becomes vital to be transparent in how data are collected, analyzed, and presented in order for others to be able to assess the reliability and validity of the results. It also becomes vital to be transparent in what judgments and assumptions about the world are included in the research itself, as well as in the assessment of the quality of the research. So if you get data that's not covering every aspect of a particular problem you're trying to observe and theorize, then you may make it upfront clear and put the caveats on the theoretical constructions, right? Although design science has a similar need for people to trust the results of the research, and reliability and validity do play roles here as well, solving problems involves an additional way of assessing the quality of the research. So if you're building something and it works to solve the problem, then that's a different issue of validity. Let me take this call for a second. Okay, so important work from the department. So although design science, as we said, when you design and build something and it works to solve a problem, then the reliability and validity play a different role. If it solves only once and doesn't repeat the performance, then you have to worry about it, right? When the purpose of the research is to address a problem, instead of understanding a phenomenon, the quality of the results can be assessed in terms of the workability of the proposed solution. Workability can be assessed by whether or not the proposed solution resolves the identified problem, or in design science terminology, whether or not the form of the artifact generates a result that fulfills the required functions as specified in the design criteria to meet the purpose of the artifact when utilized in the intended context. Multiple caveats. Basically, if somebody gives you a phone and it doesn't make calls or receive calls, or doesn't send them SMS, receive SMS, then obviously it's not a successful design, an artifact that doesn't meet the purpose that it is designed for, right? Although I would not go as far as I consider, although I would not go as far as I consider traditional science and design science as complementary, some influential scholars even argue that workability is the highest form of validity. So let's say this works in many ways. Let's say you are starting up a private company which is issuing weather forecasts. You don't have to divulge your methods, your skills or anything, but if people pay for it, use it, and are satisfied and continue to pay you for it, then that is workability, and that's better than reliability and validity in a formal sense, which operational centers, government agencies have to do because they are officially responsible for issuing forecasts for the people, and people can sue them. So they are not paying for it directly, but they are paying taxes for running the weather centers and paying the employees to produce forecasts. So you can see how complicated situations get in terms of reliability, validity and workability in real life. Okay, so let's move then to limitations of science for change. I've already commented a little on how climate science people keep on saying we must do policy relevant research, but most people don't even know what that means, because there is no one person sitting there and saying, show me whether I can make a policy out of it. Policy itself is a sausage that's made in a complicated way. So where science fits in, it depends on credibility, legitimacy, salience. If science says just government must not allow this because it's going to kill people, it's one thing. But if you say, well, it's maybe better to do it this way versus that way, then many other factors play in to how the decision is made in the end. As I said, politicians often have to make decisions, face the consequences, win elections, lose elections, and so on. Whereas as scientists, we often just give advice and not really be responsible for it. Many people on the planet are getting increasingly worried about the state of our world. At the same time, we have never been so well off in a global scale. This may seem as a paradox, but it's not. It's quite the opposite. While accelerating scientific developments since the outset of the scientific revolution have affected most aspects of human life, though to different degrees for different people, it has also spurred an equally growing hunger for resources. So we say we will solve climate change problem by moving into EVs, and EVs require all kinds of critical minerals and metals, and we're digging up the whole planet again for these, lithium, cobalt, nickel, and so on and so forth. This is in combination with the generally reductionist approach of science over the centuries, with its urge to investigate specific phenomenon or address specific problems in isolation have created this combination has created blind spots that continue to elude scientists and policymakers alike. So you often do something and then say, oops, we didn't expect that. Okay, either in terms of unintended consequences or unexpected impacts. Addressing one problem most often results in creating another, and the quite remarkable developments in terms of economic purchasing power, life expectancy, infant mortality, adult literacy, etc. have unfortunately led to a large extent being associated with unsustainable practices. So this is what Herman Daly always talked about, the gentle soul that recently moved on, that we are imagining an economic growth and sustainability as entities that have to intersect with the environment, whereas his point was that we are in the environment. Bigger the economy, less space there is in the environment to exploit resources. So that's a very different way of thinking. Maybe I should stop here and let me read this again. In addition to the fundamental limitation of reductionist approaches for grasping and addressing issues of risk and resilience for sustainable development in our complex and dynamic world, ignoring Hume's guillotine, or the French would say Hume's guillotine, or actually they might say la guillotine de Hume, is also undermining the potential of science to drive positive change. So trying to derive value from facts is problematic according to Hume's guillotine paradigm. The reason for this second limitation is grounded in the all too common habit of suggesting changes in policy and practice based on the results of a particular set of scientific studies without explicit consideration of the numerous different values that might be important in the particular context. So you have a problem, you identify the ways to solve it, you design something, and then you have to come back and see what are the various contexts in which the problem is playing out. Maybe 10 different contexts in which the same problem plays out, and 10 different cultures with 10 different values, right? Ignoring the fundamental difference between between descriptive statements about how things are and prescriptive statements about how things ought to be constitutes a real problem, and the world is full of examples where such approaches have resulted in failed policies. Often these are called wicked problems. They are ill-structured and have no solutions, so you often just resolve them, which means you have to resolve them again and again. For instance, the rapid restrictions on land use along the tsunami-affected coastline of Sri Lanka and the state of Tamil Nadu in India, which were based on the hasty assessments of public safety without considering the fundamental importance of living close to the main source of livelihood for the vast majority of people residing in that zone, and the lack of available land for resettlement close enough so they can continue with the same livelihood or alternate livelihoods. This becomes important because the tsunami is a high impact, low probability event. Another tsunami may not come for a very long time, multiple generations, so then people will feel like they were cheated by pushing them out of their livelihoods. So here fishermen, boats and nets on the beach in Tamil Nadu as a prop. This is just a few months after the tsunami. Have no doubt that the tsunami really knocked the wind out of them, because I think some 10,000 people were killed along the coasts of Tamil Nadu, which is not a small number, and they had never seen such a wall of water in their lives. So they were scared, but now by 2024 obviously they would have forgotten, or there is a new generation which didn't experience it or doesn't remember it, and so on. So these are tricky things. So we'll come back and conclude this chapter on reliability, validation, workability, and so on. Okay.